Our next topic is issues in decision tree learning. So these are the main things we will be discussing one by one. The first one is avoiding overfitting the data. So in that reduced error pruning and rule post pruning. So we will discuss uh, incorporating a continuous valued function. Continuous valued function means numbers like 1, 2, 3, 4, and other real numbers and fractions. Alternative measures for selecting attributes. If we don't want to follow the gain based information gain based selecting attribute, so we are telling that we may go for something else. Next one is handling training examples with missing attribute values. So if we have a data set and the values are missing in some of the instances, what can we do? So the handling attributes with differing costs. So so we'll introduce a new term called cost here. Okay, so we may take it as a computational cost and many other types of resource cost. Okay, so many other types of cost. So instead of selecting an attribute based on only on information gain, so we'll consider cost also. So first one, if you observe avoiding overfitting of data, so we'll go to that part. So first point, avoiding overfitting of data. First we will understand what is overfitting the data. We'll just take a real world a vague example. Suppose we are studying for examination and we by heart all the questions without understanding it. So in the test, if we get the same question, we'll do well. So if we get some twisted question, we will not do well, right? So that is overfitting of data. So whatever hypothesis we have created, that will be become tailor made for only the data set. Okay, so we'll see the definition. Given a hypothesis space H, hypothesis H is set to overfit the training data if there exists some alternative hypothesis H dash such that H has a smaller error than H dash over the training examples, but H dash has a smaller error than H over the entire distribution of instances. What does this mean? So in the hypothesis space, that means a collection of hypotheses which are consistent with the data set, there are two hypotheses H and H dash. Okay, so if we see the accuracy of prediction of H over the training data, so it is good, then better than H dash. But if you take H dash has better accuracy over entire distribution of instances. Entire distribution of instances means test data also or a new instance also, it has good accuracy than H. Okay, so let's connect it to our older examples. So there is student A, student B. Okay, so A is said to be overfitting the data if the performance of repeated question in the question paper, so A will do well. So if we ask only the by hearted question, A will do well than B. But if we ask twisted question over entire knowledge of the syllabus, if we ask the question, then B will do well. Okay, so that means that A has overfitted the data. Okay, so the student A only knows bookish. Okay, so in the similar way, we have H and H dash hypothesis. H is said to be overfit only whenever H performs very well than H dash for a given data set. Okay, but H dash perform well over H whenever new instances have come. So H dash performs in the outer world also. H performs well only on the data set. So then we say that H has overfit the data. Okay, so this will be the meaning of overfitting the data. So we want to avoid it. So how do we avoid it? We will see. Just for the illustration of overfitting of data, So we'll assume that we have applied ID3 algorithm to some medical data set. Okay, so whenever the tree grows to a much greater height, so it tends to overfit the data. Okay, so we have a graph, so straight away taken graph from the author, so which gives accuracy versus size of the trees in terms of number of nodes. Okay, so if you observe that one, so as the size of the tree grows on training data, the accuracy increases. It may even reach like 85%, 87%. But so as the size of the tree grows, it tends to overfit the data, and on test data means new instances which are not involved in the training. So this on the test data, the accuracy remain same or it starts decreasing. It will not grow. Okay, so this is an illustration that the accuracy of the prediction on the new data either will be same or decreases as the hypothesis, or in this case it's the size of the tree, or hypothesis becomes more fine tuned. Okay, so if the more that there is should be an optimum training always. If we train very much, okay, so with a lot of data, and the hypothesis may become hypersensitive, and it will classify very well the test data, the training data, but it will not classify to that accuracy the test data means a new instance, okay, which was not involved in the training data. The training data, if you supply, it will classify well. Okay, so but if you give a test data, it will not, the accuracy will decrease. So this is an illustration of this is the reason we need to reduce overfitting of data. So as we are talking about decision tree learning, overfitting happens in all kinds of hypotheses, all representations of hypotheses, maybe a tuple form, decision tree form, or maybe a neural network form. So in all the representation of the hypothesis, overfitting happens, but in this case we are talking about decision tree. So there are two approaches to avoid overfitting of data. So what the tree should be of optimum height. Okay, so if it is less, the accuracy decrease. It is if it is more than threshold height of the tree, then it overfits the data. So the first approach is that stop growing the tree earlier before it reaches the point where it perfectly classifies training data. So if you are telling that our hypothesis is perfectly classifying the training data, it may have overfit the data. Okay, so second one, approaches that allow the tree to overfit the data first, then post prune the tree. Okay, so pruning means removing the nodes from the tree. So there are two: either don't allow them to allow the decision trees to grow beyond a threshold level, okay, threshold size, or allow it to grow it completely and then start pruning the branches of the tree. Okay, so decision tree start the pruning of the branches. So first action is taken earlier, in the second method action is taken later. So we will explore both of them. A key challenge we have is we have to determine on what basis we decide that this is the correct tree size. Okay, so if the tree size is very small, the accuracy may decrease. If the tree size is very big, it may overfit. So we have to find a optimum tree size. So the first method is use a separate set of example, okay, distinct of training example, that is test data it is talking about, okay, as to evaluate the utility of post pruning nodes from the tree. Okay, so what we will do is we remove some branches of the decision tree and check it on a test data. So if it performs well on the test data, that means that tree is good. Okay, if the accuracy decreases, that means pruning was wrong. Okay, so if the accuracy does not decrease, if it performs well on the test data, then pruning has been successful. Post pruning means first allow it to grow, allow tree to grow completely, then start chopping off the decision trees branches. Okay, so the second option is use the available data for training. Okay, completely use all the data. Don't keep some test reserve some data as test data. So what happens here, how do we get the test data? So usually what do we do, suppose we have 10 instances for example, then use 8 of them for training, use 2 of them for testing. So if we are having a 80-20 ratio, otherwise we can have 50% for training, 50% for testing. Many ways are there. So that's the so use all available data for training, don't reserve any of the instances for testing. So but apply a statistical test to estimate whether adding a node or removing a node is likely to produce an improvement beyond the training set. Okay, so statistical method is usually chi-square test. Those are the statistical methods, but we don't, it's out of scope of the lecture and also the syllabus. So so you can understand it as understand it like this. So you use all the data for training. Okay, so then find out through chi-square test or some other statistical methods whether it is good to add more nodes or remove some nodes. So next last method is we will use some measure of complexity for encoding the training examples and the decision tree, halting the growth of tree when this encoding size is minimized. Okay, so what we are doing here is for example in the language of tuples hypothesis we are telling. So we have a target that we will be able to classify our instances with only 2 attribute values. Okay, so only 2, others we don't need. So that's the if we are able to achieve it, then stop the decision tree. Okay, so we start constructing the decision tree. Decision tree is done, so then we start testing whether it is possible. Suppose we have 3 nodes to predict a instance, so then we start testing that if we have only 2 instances, 2 nodes. Okay, so whether it classifies correctly or not, what is the accuracy? If the accuracy is good, keep only that much. Okay, so the way of representing that we need only 2 nodes, that's the encoding technique. Okay, so if this much is enough for this point, because again so we just want to list the methods for avoiding overfitting, and we don't have to go too deep into it. So we the main uh, the main way we have found to reduce overfitting in decision trees is pruning the branches. Okay, so we have discussed ways for it. Now we will take we will focus on 2 of the methods. One is reduced error pruning. So we prune them. So it is same as we talked before. So we will remove a node. Okay, so we will keep the classification, most common classification, remove the node, attach yes and no for it as a leaf, then test it whether the tree is classifying with the same accuracy or the better accuracy. So it is doing, if it is doing with the same accuracy, if the accuracy is not decreased, then we don't want that node. Okay, so we have a tree and we have it is made up of nodes and leaves. Okay, so remove one node, we remove one sub branch for example. Okay, so then test the tree. If it performs well, keep the same tree because it's performing well. The performance should be at least same, if not better. Okay, at least same. So if it does not perform well, if the accuracy decreases, then reject that removal of node and keep the tree as it is. So we'll read the definition. Pruning a decision node consists of removing the subtree rooted at the node, making it a leaf node, and assigning it with the most common classification of training example. Yes or no leaves we have to attach. So nodes are removed only if the resulting pruned tree performs no worse than the original over the validation test. Okay, so the new tree what we have obtained by removing the sub branch, it should perform at least as same as the fully grown tree. So only then we will keep it, we will accept it, otherwise we will not accept it. So just an instance, same graph, accuracy versus size of the tree. So we can observe that on training data, so the more we train and size of the tree, the accuracy is increasing. So on test data, again it was around like 70%. And on test data during pruning, uh, somewhere it started behaving come down. Okay, pruning means we don't so there is always a optimum tree. Okay, so we have the tree is big, it has overfit the data. So the we start pruning it. So the pruning should be one or two pruning, normally one or two branch maximum. So if we start pruning means if we are cut off all the branches of the tree, what will happen? The accuracy will decrease. So that's what it is showing in the graph. So just a illustration and also the content for your examination. So the second one is a rule post pruning. So we'll see how we prune the tree after the fully grown tree is overfitting the data. So first what we'll do, uh, so in for the decision tree from training set. Okay, so create the decision tree, growing the tree until the training data is fit as well as possible and allowing overfitting to occur. So it will overfit. Then convert the tree. So that created tree, learned tree means created tree into an equivalent set of rules by creating one rule for each path from root node to leaf node. We'll see the example next. Then prune each rule by removing any preconditions that result in improving its estimated accuracy. So we'll see here. Okay, so I will see that. So if outlook equal to sunny and humidity equal to high, then play tennis is no. So we can see the decision tree. That's one path. Okay, so outlook equal to sunny, humidity equal to moderate, then play tennis equal to yes. That's another path. Okay, for each and no leaf, there is one path from the root, and we have taken one path. Okay, observe the remember the tree. So here we have taken one path, that is outlook equal to sunny and humidity equal to high. So for so this is converting it to a rule form. Okay, so first we had a decision tree. From that, for example, like this, we have converted into a rule form. Then there are two preconditions here: outlook equal to sunny, humidity equal to high. If that is the case, then play tennis is no, right? Then outlook equal to sun, you remove outlook equal to sunny and check only if humidity equal to high, only this information is enough for classification. Or so remove humidity equal to high, so check whether only outlook equal to sunny is enough for the classification of play tennis. If that is the case, then we can remove that node and the tree will be pruned, right? So this is what is telling. So convert the tree into equivalent set of rules. So as we have seen, then removing prune each rule by removing any precondition that result in improving its estimated accuracy. Okay, so we'll just go through again. We have a tree. So outlook equal to sunny and humidity equal to high is no. So that's one path. Outlook equal to sunny, wind equal to strong, equal play tennis equal to no. So that's another part. Outlook equal to overcast, play tennis equal to yes. That is one path. Outlook equal to sunny, humidity equal to normal, the play tennis equal to yes. That is another path. So we have many of the, so each of the branch from root to leaf, that becomes a path, right? So that's how we go on making rules. For example, this. Okay, so after that step, remove outlook equal to sunny and see whether it classifies properly, or remove humidity equal to high and check whether it classifies properly. If yes, then we don't need humidity equal to high, or we don't need outlook equal to sunny. So we have pruned the node. So what is the advantage of converting our decision tree to rules before pruning? Is the first thing is, so observe, suppose we are pruning a decision tree and we are removing a node, that means that we are removing that entire subtree. Okay, so here if you are removing some attribute, okay, so we are only removing that path, that's it. Okay, so for example, outlook equal to sunny, humidity equal to high. So humidity equal to high is not needed, let's assume. Okay, so outlook equal to sunny, plate n is equal to no, so just assuming. Okay, uh, but for classifying it as yes, we may know outlook equal to sunny and humidity equal to normal, we may need more information, right? So classify it as no, we need less information. To classify it as yes, we need more information. Suppose this is possible only in a rule based. Okay, so we have greater control over the tree pruning when we convert it to a rule base. Okay, when we convert from decision tree to rules. Okay, so what we are doing, so we are deleting only one path instead of entire subtree. So that's what the point is telling. So if you are keeping it as a decision tree, then we have to remove entire subtree. So if we are converting it to rules before pruning, to check for pruning, we have to just take out one attribute, one path. Okay, so we have greater control over decision tree pruning. So if we are converting it to rule based one, and also converting it to the rules improves the readability and easier to understand. We will be discussing the second, third, fourth and fifth issue in the decision tree learning in the next video. Now we will discuss the uh, last 4 points: incorporating continuous valued function, alternative measures for selecting attributes, handling training examples with missing attribute values, and last one, handling attributes with differing costs. Incorporating a continuous valued function. So what are continuous valued numbers, values? Okay, so you can observe here temperature 40, 48, 60, 72, 80, 90. These numerical values, these are continued values, continuous values. So if we look at the table in the right, we see sunny, overcast, and these are discrete values. So we know that our decision tree classifies or needs only discrete values. So uh, what if there is continuous values in the data? What we have to do? So we may transform continuous values to discrete values. So what are the attribute values of temperature? Hot, mild and cool. So let's assume that 80 to 90 is hot, 60 to 70 to 90 is hot, 60 to 70 is a mild, 40 to 50 is cool. Suppose we make a range of numbers and assign a discrete value to it. Okay, so this is how we are able to change our numerical values to a discrete value, discrete attribute value. So the second issue now which we are seeing here is, so if we have a continuous value attributes, what we have to do with it? So what we have to do, we need to convert them into a, from continuous valued attributes to discrete valued attributes. So let's see the points here. ID3 target attribute value is predicted by learned tree must be discrete valued. So our tree needs value attribute values which are discrete. So the attribute tested in the decision nodes of the tree must also be discrete values. So this can be accomplished by dynamically defining a new discrete valued attributes that partition the continuous attribute value into a discrete set of intervals. So what we did now, 40 to 50 is cool, 60 to 70 is mild, 70 to 90 is hot. So like that, the intervals we defined into a new discrete value, right? So that's what it is talking about. So dynamically define a new discrete valued attributes and map them to the continuous values. So at last, for an attribute A, so that is continuous valued, the algorithm can dynamically create a new boolean attribute, yes or no. So boolean attribute, if you want to do, so yes or no. So if um, that boolean attribute is true, if it is less than the threshold, otherwise false. Okay, so if you want only two attribute values, yes or no, or hot or cool, only two attribute values, then take a threshold, and below that a continuous value, one type of discrete value, above that one kind of discrete value. So if there are several discrete attribute values, if we want that, so then we create intervals between that continued valued numbers and assign discrete values to those things. Okay, so this is the example. So we have continuous values for temperature, so we make intervals of numbers, and for the each of those intervals we can assign hot, mild and cool. So this is an example, and this is the second point. So how to deal with the continued valued function in decision tree learning. The third point simply says that as our ID3 algorithm has naturally a bias towards information gain, so we may explore other strategies also. So it's a natural bias in information gain that favors the attributes with many values over those with few values. That means which has higher information gain. So we need to explore other strategies too. The fourth one is handling training examples with a missing attribute values. So suppose we have a data set, and some of the attribute values are missing. So we need to fill that. Can we fill that? So one idea is so it is common to estimate missing attribute value based on other examples for which the attribute value is known. So we have a missing attribute value for an instance. So see a similar instance, and check out what is the attribute value there, and fill up the same here. Okay. So the next strategy is to assign the most common value. Okay, so suppose temperature equal to cool is the most common value in the data set, then fill the most common value. Okay, so fill temperature equal to cool for the missing attribute value. The next one is a more complex procedure is first find out the probability of probability that an instance have a attribute value of x. Okay, so suppose in temperature there are three possible values. um, so hot, mild and cool, and there is a missing value, let's assume. Then we will assign probability to hot, mild and cool through a statistical method. So we don't have to explore what is the statistical method. A statistical method is used. Okay, so we'll assign a probability to hot, mild and cool. Whichever has the highest probability, we will fill that value. Okay, so these are the techniques. So what we have seen here, so if we have a data set, and we are building a decision tree, and we have an issue. What is that issue? In the data set we have missing attribute values. So how to fill that? So fill that with the most common attribute value, or similar instances, what was the attribute value, so fill that. Otherwise statistically find out what are the probabilities for the values of that attribute, and the value which has the highest probability, use that one. So last one, last issue, handling attribute with the differing costs. So we only have checked out information gain, but if for a large data set like GBs of data set, the computationally intensive it may be. That means it may consume much computational power. Though the information gain is more, that particular tree. So remember that in a hypothesis space there are many which are consistent with the data set. So ID3 is selecting one particular tree, constructing one particular tree among that one. Now, if the cost of that tree is very much more, if it is though the attribute value has the highest information gain, so we may have to associate, we have to find a way to associate cost with also information gain. So we need to modify our ID3 to account cost too instead of only information gain. How can we do that? So simply divide the gain by the cost. Okay, so if the cost is more, then that ratio will come, gain to cost ratio will come down, and if cost is less, then that gain to cost ratio will go up. So whichever has the highest gain to cost ratio, use that one. Okay, so we have an example of one example. Okay, so take the square of the gain, divide it by cost. So if the denominator is more, if the cost is high, the total value of this will come down. So if the denominator cost is low, the total value of this equation becomes higher. So by this we are accounting cost to into our gain instead of only considering the gain. So these are the issues with the decision tree: avoiding overfitting of data, and how to incorporate continuous valued attributes. So alternate measures of selecting attributes, handling training examples with the missing attribute values, handling attributes with differing costs. Okay, so these are the issues in the decision tree. In examination, if you get a question, explain issues in the decision tree, these are the main headings, and within that you go on explaining what is presented in the slides.